Good day. Now we will be answering problems from Chapter 28, Sources of Magnetic Field. We will answer problem numbers 28.59, 28.61, and 28.68. First problem, problem 28.59. A long straight wire carries a 13 ampere current. An electron is fired parallel to this wire with a velocity of 250 km per second in the same direction as the current, and that is 2 cm away from the wire. A. Find the magnitude and direction of the electron's initial acceleration. B. What should be the magnitude and direction of a uniform electric field that will allow the electron to continue to travel parallel to the wire? And part C. Is it necessary to include the effects of gravity? Justify your answer. So in this illustration, we included the direction of the magnetic field. So this was determined by using the right hand rule. So this is my right hand and the direction of the current is towards the right. And this is the direction of the magnetic field. So above, it is directed out of the plane, and below, it is directed into the plane. To answer this problem, we will use these constants. So this is the magnitude of the electron's charge, the magnetic constant, and the mass of the electron. So for part A, we are going to find the magnitude and direction of the electron's initial acceleration. So by Newton's second law, acceleration is equal to the force divided by the mass. And the magnitude of the force acting on the electron due to the magnetic field of the wire is given by this equation. Now, substituting F with this F, we will get acceleration is equal to the absolute value of the charge multiplied by the velocity and magnetic field sine phi all over the mass. Then, for the magnetic field of a long straight current carrying conductor, the formula is magnetic field is equal to the magnetic constant multiplied by the current over 2 pi r. Now let's substitute B with this B, and this will give us this portion. And for the Q, we have the electron's charge. So the magnitude is this. Substituting the value, so this is the electron's charge, the velocity of the electron, this is the magnetic constant mu naught, and the current divided by the mass of the electron, 2 pi, the distance of the electron from the wire. And calculating this will give us 5.7 times 10 to the 12 meter per second squared of acceleration. So that is the answer for part A. And the direction will be away from the wire, because the direction of the acceleration is the same with the force. So the direction of the acceleration is the same with the force, or same with the direction of the magnetic force. By right hand rule, as shown in this figure, the direction of V cross B is toward the wire. However, since Q is negative, then the direction of the force is away from the wire. Thus, the direction of A is away from the wire. For part B, we are asked to find the magnitude and direction of a uniform electric field that will allow the electron to continue to travel parallel to the wire. So the electric force must balance the magnetic force, or they must be equal in magnitude but opposite direction. So the formula for electric force is this, while the formula for magnetic force is this. Equating the two, since they are equal in magnitude, will give this. For the electric force, we have the charge of the electron times the electric field, and it is equal to the magnetic force, which is charge times the velocity times the magnetic field. So we will cancel E, or the charge of the electron, and it will give us E is equal to velocity times the magnetic field. So by this, we will find the magnitude and direction of the electric field. We know that the magnetic field of a long straight current carrying conductor is mu naught I current over 2 pi r. So let's substitute B with this B, giving us velocity times mu naught I over 2 pi r. Substituting the values, so this is the velocity of the electron, the magnetic constant mu naught, the current 2 pi, and then the distance between the electron and the wire. Solving this will give us 32.5 Newton per Coulomb. So this is the magnitude of our electric field. And the direction is away from the wire. Because the magnetic force is directed away from the wire, so the force from the electric field must be toward the wire. So as stated here, they are opposite in direction. However, electron is negative, so the electric field must be directed away from the wire to produce a force in the desired direction. For part C, is it necessary to include the effects of gravity? Justify your answer. So, in solving the force acting on the electron due to gravity, we have mg. And substituting the value, this is the mass of the electron, multiplied by the acceleration due to gravity, this will give us approximately 10 to the negative 29 Newton. On the other hand, the force acting on the electron due to the electric field is given by this force times force equal to charge times the electric field. So the charge of the electron is 1.6 times 10 to the negative 19 Coulomb multiplied by the electric field, which is 32.5 Newton per Coulomb. This will give us approximately 5 times 10 to the negative 18 Newton. We can see that the electric force is approximately 5 times 10 to the 11 of the the force due to the gravity. So we can neglect gravity. Next problem, problem 28.61. An electric bus operates by drawing direct current from two parallel overhead cables at a potential difference of 600 volts and spaced 55 centimeters apart. When the power input to the bus motor is at its maximum power of 65 horsepower, what current does it draw, and what is the attractive force per unit length between the cables? So, finding the current I that the bus's motor draws. So, we know the formula for I is equal to P over V, the power over the potential difference, and we need to convert the power to watts. So 1 horsepower is equal to 746 watts. So to convert it, we will multiply the two, and using this formula, we will divide it by the potential difference, which is 600 volts. Solving this, we will get 80.8 amperes. For part B, we are asked to find the attractive force per unit length between the cables. And given the formula for two parallel wires, the force between them is magnetic constant multiplied by the length, current 1 times current 2 over 2 pi r. Rearranging to find the force per unit length, so we have force per unit length here, and that is equal to the magnetic constants times the product of the two current over 2 pi r. Now, substituting the values, we have the magnetic constant here, which is this, and the current between the two, or the current, is 80.8 ampere, and divide it by 2 pi, the distance between the two wires. Solving this, we will get 2.4 times 10 to the negative 3 Newton per meter. So this is the attractive force per unit length. between the two cables. For the last problem, problem 28.68. Calculate the magnetic field, both magnitude and direction, at a point P due to a current I which is 12 amperes. Segment BC is an arc of a circle with radius 30 centimeters, and point P is at the center of the curvature of the arc. Segment DA, which is this, is an arc of a circle with radius 20 centimeters, and point P is at its center of curvature. Segments CD and AB are straight lines of length 10 centimeters each. So to solve this, we must first determine the direction of the magnetic field due to arc DA and arc BC at point P. We will be able to determine it by right-hand rule, since the direction of the current on arc DA is from D to A. The direction of the magnetic field will be directed into the plane. While for arc BC, the direction of the current is from B to C. Therefore, the direction of the magnetic field due to arc BC is directed out of the plane. The magnitude of the magnetic field at the center of a circular loop of radius r is given by this formula. Magnetic field is equal to the magnetic constant times I all over 2 pi r. Since each arc is only one-third of a complete circle or loop, then we will only consider one-third of the magnetic field. Simplifying this, we have mu naught I over 6 pi r. Now, let's calculate the net magnetic field at point P by adding the two magnetic fields due to arc DA and due to arc BC. Since the magnetic field due to arc DA is directed into the plane, it is positive, while negative for the magnetic field due to arc BC because it is directed out of the plane. Substituting the value for the current, we have this, and substituting the values of R, and calculating this, we will have 4.19 times 10 to the negative 6 Tesla, or 4.19 micro Tesla. So that is the magnitude of the magnetic field at point P. Now, for the direction, since arc DA has smaller radius compared to arc BC, by this equation, we can see that the smaller the r, the bigger will be the magnetic field. Therefore, the magnetic field of arc DA is greater than the magnetic field of arc BC. The net magnetic field points will be into the page at point